Biomedical waste management is a critical discipline in healthcare and environmental safety, focusing on the systematic handling of hazardous materials generated during medical activities. This field ensures that waste produced by hospitals, clinics, and laboratories does not pose a risk to public health or the environment. Proper management involves a rigorous chain of custody, from the moment of generation to final disposal, utilizing specialized protocols to prevent the spread of infectious diseases and chemical contamination. Throughout this presentation, we will examine the sophisticated engineering and regulatory frameworks that govern the safe destruction of these materials, ensuring that every step of the process adheres to international safety standards. Advanced treatment and destruction technologies represent the pinnacle of modern waste engineering, focusing on the sophisticated methods used to neutralize hazardous biomedical materials. This section explores the technical evolution from simple disposal to complex thermal and chemical destruction processes. These technologies are designed to handle various waste streams, including anatomical, cytotoxic, and infectious materials, ensuring they are rendered completely harmless. By employing the advanced engineering, these systems minimize environmental impact while maximizing safety, representing a shift toward more sustainable and efficient healthcare waste management solutions that meet modern regulatory requirements. Dual objectives of destruction define the core goals of any advanced waste treatment system. First, technologies must achieve absolute biological sterilization of all pathogens. This means every bacteria, virus, and spore must be completely deactivated to prevent any risk of infection or disease transmission. Second, these systems must simultaneously maximize the volumetric and physical reduction of the waste. By significantly reducing the size and mass of the waste material, facilities can minimize the footprint required for final landfilling, making the entire disposal process more efficient and manageable for long-term environmental sustainability. High-temperature incineration serves as the primary mechanism for annihilating yellow-category anatomical and cytotoxic waste. This process involves extreme heat to break down complex organic materials into their basic components. Furthermore, incineration is treated as a complex industrial emissions challenge, not just a disposal method. This perspective shift is crucial because the combustion of medical waste can produce hazardous gases. Therefore, modern incinerators are designed as high-tech chemical processing plants that prioritize the containment and treatment of gases to ensure that nothing harmful is released into the surrounding community or the broader ecosystem. Emission control regarding dioxins and furans is a critical safety component of modern incineration. Strict statutory limits, specifically 0.1 nanograms of toxic equivalents per normal cubic meter, force incinerators to use advanced scrubbers. These scrubbing systems are engineered to capture microscopic pollutants before they exit the stack. This rigorous filtration prevents the release of endocrine-disrupting chemicals into the atmosphere. Because dioxins and furans can persist in the environment and interfere with hormonal systems in humans and wildlife, maintaining these ultra-low emission levels is a non-negotiable requirement for any facility operating today. Secondary chamber retention is a technical requirement where incinerators must maintain extremely high temperatures with a 2-second gas retention time. This specific duration in the secondary combustion zone is vital for thorough treatment. It ensures the total oxidation of volatile organic compounds before stack release. By holding the flue gases at high heat for at least 2 seconds, the system guarantees that even the most resilient chemical chains are broken down into simpler, safer molecules, like carbon dioxide and water vapor, effectively eliminating the risk of releasing unburnt hazardous organic pollutants into the air. Plasma pyrolysis gasification is an eco-friendly alternative using electrical arcs in an oxygen-starved environment. Unlike traditional burning, this process uses a plasma torch to create intense heat, reaching temperatures comparable to the surface of the sun. This intense energy decomposes waste down to basic molecular structures with minimal toxic smoke. Because the process occurs in an environment lacking oxygen, it prevents the formation of many common pollutants associated with combustion. The result is a clean synthetic gas and a glass-like slag, representing one of the cleanest methods available for destroying complex medical waste. Autoclaving and hydroclaving are methods that use high-pressure steam to reliably destroy cellular proteins in red category plastics. These technologies utilize the power of moist heat to penetrate waste materials, ensuring that every surface is exposed to sterilizing conditions. This process is recognized as a highly effective, non-polluting mechanism for sterilization. Because it does not involve combustion, there are no atmospheric emissions to manage. This makes it an ideal solution for treating plastic items like tubing and containers, which can then be safely handled or recycled without the risk of carrying infectious agents. Mechanical shredding is a vital post-treatment step where post-sterilization maceration renders plastics and syringes completely unrecognizable. By physically breaking down the treated items into small, uniform pieces, the waste loses its original form. This step fundamentally disrupts the illegal resale of used medical devices. In many parts of the world, the scavenging and illicit repackaging of used syringes is a major public health crisis. Shredding ensures that once a medical device is used and sterilized, it can never find its way back into the market, thereby protecting the public from contaminated equipment. Incinerator ash management is the final step in the thermal destruction process. Bottom ash concentrates toxic heavy metals post-combustion, as these elements do not evaporate or burn away. Because this ash contains concentrated levels of substances like lead or mercury, it must be safely disposed of in secure, heavily lined hazardous waste landfills. These specialized landfills are designed with multiple layers of protection to prevent the heavy metals from leaching into the groundwater. Proper ash management ensures that the toxic residues of the incineration process are permanently isolated from the environment. Thank you for your attention throughout this detailed exploration of biomedical waste management and advanced destruction technologies. We have covered the critical importance of sterilization, the engineering behind high-temperature incineration, and the vital role of emission controls and mechanical shredding in maintaining public safety. Understanding these complex processes is essential for anyone involved in healthcare administration, environmental science, or public health. By implementing these advanced technologies, we can ensure a safer, cleaner future, where medical waste is handled with the highest level of professional and environmental responsibility.